Hello, everyone. So I'm Chuan-Kai. So this is a joint work with my student, the first author, and also a colleague of my university. Professor Lai is also here. So I'm from the Computer Graphics and Multimedia Laboratory. It's the Department of Information Management, National Taiwan University of Science and Technology. So this is the title. So the title is called Lightweight American Sign Language Recognition Using a Deep Learning Approach. Okay, so this will be the outline. So I'll first start with the introduction and talk about some related works, and followed by the proposed methods, and show you some of the experiments and the results that we have got, and finally conclude with a conclusion and point out some future works. Okay, so this is like the motivation. So actually, we know that I think in around 2011, only in America. So for the American populations, I think it's around 11 million people, they have this problem of hearing. So because of that, we see this communication barrier between the hearing impaired people and normal people. So that's why we want to do this kind of research, like a sign language recognition. And also because of this advancement in computer field, and this makes the recognition of sign language possible. However, because of this computation complexity and hardware limitations, so this kind of sign language recognition is still not that convenient to be implemented. And also we noticed that if we try to reduce the complexity, that may cause the accuracy to be decreased. Okay, so basically in this paper, we try to propose two approaches. The first one is that we try to start from some publicly available data set, okay, and then try to use media pipe to extract key points and combine it together with the LSTM. And also we will try to make use of the image data and try to perform the training from scratch. So that's sort of the first approach. And the second approach, we try to make use of some pre-trained model. It's called the MoViNet. And we try to use the lightest weight version of it and try to fine tune. And so basically we are using two kind of approaches and try to compare the performance. And for the second one, the reason we try that is because it's light enough to be run, okay, on a cell phone. So we want to build an app essentially. Okay, so to talk about some related works. So basically there are four types. The first one is action recognition. So it's quite active, and for some of the state-of-the-art models, they offer high recognition accuracy. And some of them, I think they include I3D, C3D, and two-stream approaches. The problem is its cost very expensive computation. And the second type of related works is related to sign language recognition. So basically, we are using computer to perform the recognition. And there are already some approaches published. They try to make use of machine learning or deep learning approaches. And the third type is called human pose estimation. So basically, we are trying to predict the key points on the target body. And we can also try to predict the smaller body parts, such as the fingers. And examples of such include media pipe, YOLO pose, or open pose. And finally, that's the MoViNet. So it's a recent state-of-the-art lightweight action recognition network. And like I mentioned before, it can have a very light version, or the complexity can be very, very small, such as the model of MoViNet V3. And if we try to check the complexity, the accuracy, it can be quite comparable to a very complex model of X3D XS model. Okay, so this is to talk about the first approach. So essentially, we are making use of the MS ASL sign language data set. So it's composed of this sign language videos. And we tried to download it 2 years ago. And essentially, there are like 1,000 classes, meaning we are talking about 1,000 sign languages. But that's like too much. So for this research, we only concentrate on the sort of the most frequent 100 classes. Okay, and we try to randomly sample them to be 16 frames per data. And we also try to perform data augmentations by doing horizontal flipping, okay, to increase the data set a little bit. And from this video data set, we try to generate two kinds of data. The first one is the key points. So it includes the XY coordinates of this body joints. And we only focus on the hands and the arms because they are mostly related to the sign languages. And also we add the elbow angle. So, so the final data type is of this like n by 16 by 146. N means the number of data we have. And the other type of data we generate from the data set is the RGB data, means the image. Okay, so the images are scaled to become 172 by 172. And also together with all the frames and together with all the data. So the data is in the form of n by 16 by 172 by 172 by 3. 3 means the RGB channels. Okay, so this basically highlights the architecture that we use for the first approach, the key points plus LSTM. So like I mentioned, we try to use media pipe to extract all the key points and then use LSTM with different number of layers. And you can see the parameters here. And after that, we send the data to the dense layers and finally softmax layers to classify into that 100 classes I mentioned. And for the second approach, essentially, we take this RGB data and then try to use MoViNet A0. So that's a pre-trained model, and try to fine tune it and then have the data, have the classification result outputted by using a softmax. So this is the training setup. So as you can see, actually we are using Google Colab to help us to do this training. Okay, so this is the sort of the spec we select using Google Colab. And so these are all the training parameters for your reference. So like I mentioned, we train this data from scratch, and it takes about 18 epochs. And if we try to make use of all the data we have, and the training and the validation split is 80% versus 20%. We use the Adam optimizer and the learning rate, something like that. And also the loss function. And this is the result we got. So we try to measure the top 1 accuracy and the top 5 accuracy. And as you can see here, if we focus on the top 5 accuracy, of course, should be higher than top 1 accuracy. Okay, and for the training accuracy, usually it should be higher than the validation accuracy. So probably you can see that I think it's around 55 epochs also, the result is already stabilized. And this is trying to see the effect of data set size. What we have done is trying to make use of just 80% of the data and to see how that impacts the accuracy. So as you can see here, the accuracy actually doesn't change much. Okay, so for example, the blue line is the top 1 accuracy. And if we try to make use of only 80% of the data, so it drops just a little bit to this brown line. Okay, something like that. Similar things happens if we are talking about type 5 accuracy. Okay, so if we just use 80% of the data. Okay, so this is the training parameters for the MoViNet. Okay, so like I said, actually, this is a pre-trained model and we just try to fine tune it. Okay, so we are making use of this MoViNet lightweight version. Okay, the A0, the lightest weight version. And these are, anyway, the parameters that we use. And we also try to split the data because the data set is huge and we try to do it iteration by iterations. Okay, so basically they are, like I said, the data set is huge. So we try to divide it into 10 parts. And for each iteration, we try to make use of 1 part and try to do it like incrementally. So as you can see, if we are talking about the top 1 accuracy and top 5 accuracies, as iteration goes on, the accuracy will increase. Okay, and this is just to compare the accuracy of MoViNet A0 and MoViNet A3. A3 is a heavyweight version, if you will. So A0 is a lightweight version. So in the future, we want to make it a mobile application. So that's why we want to focus on lightweight version. So that means we also want to study sort of the accuracy difference between this lightweight version and the heavyweight version. So for heavyweight version, that's the A3 version. Although it can offer higher accuracy, but like I said, it's more heavyweight. So on the other hand, if we just use a lightweight, I think the accuracy that we can achieve is still quite comparable. Okay, anyway, so this just to see the relative performance on all kinds of sign languages, all kinds of signs that we perform. And we try to examine what happens to those classes that we have low accuracies. So this is just to show the accuracy distribution. Okay, so after we do this, we found out that actually for some of the classes that we have relatively low accuracies are like for some of the signs, like man or woman. Okay, so we try to further examine what happens, and it turns out we can see that for some of the sign languages, like man, as you can see here, on the first row, the left part, they all mean man. Okay, but their hand shapes and movements are quite similar. So that's sort of the reason for this misclassifications. So similar things happen for other sign languages as well. So this will be very challenges to deal with these similarities. Okay, so for this slide, we just want to compare the performance of our two approaches with other methods. So as you can see here, I3D, okay, can offer the highest accuracies, no matter we are talking about top 1 or top 5. And our approaches, the bottommost two approaches, the Keypoints plus LSTM, or the other one, pre-trained model plus fine-tuning, although they can not offer the accuracies as high as I3D, but I must point out that for I3D, it's a very, very heavyweight model. So that kind of model cannot be easily ported to a mobile phone. So that's the problem. And that's also why we want to focus on this kind of approaches. Okay, so we also want to discuss about the complexity. So this complexity is in terms of mega flops or floating point operations. So in terms of complexity, as you can see here for I3D, it's quite high. And but for ours, if we are talking about MoViNet, actually we can exactly measure that. So it's quite light compared with I3D. And for LSTM, you can see here we have a number is called C plus 108. The reason is that we cannot have a very accurate estimate of this media pipe cost. So that's we just use C to denote that complexity. But we believe because media pipe can be run in a real-time manner, so the cost should be relatively low. Okay, so anyway, compare with I3D, I believe our complexity is low enough. Okay, but at the same time, we can still provide quite comparable accuracy. Okay, so finally, we just want to point out the limitations that of this research. So currently, we only have limited number of data. Okay, and for media pipe, it's still not perfect. Sometimes it can still like have some errors. And the most serious limitations actually is that we want to port this model to a mobile phone. I think it's already light enough, but the problem is some of the libraries still not available. So we are still working on it. But theoretically, we have sort of proved that this model is already light enough to be able to run on a mobile phone. Okay, to conclude the talk, so we have explored the possibilities of creating a lightweight model using this MS ASL data set using two different approaches. The first one, like I said, is the Keypoints plus LSTM, and the other one is to fine-tune a pre-trained MoViNet A0 model. And for the top 1 accuracy, we can achieve about 70%, and for the top 5 accuracy, it's about 85%. So although the achieved accuracy is still lower than the I3D model, but like I mentioned before, I3D model is quite heavy, so our models are relatively light and still can provide reasonable accuracy. So in the future, like I have said, so we want to make it a real mobile applications. And of course, the accuracy can still be further improved. And we will also like to combine it with some NLP model to further improve the usability. So That's all for my presentation. Thank you.